So all of the previous page was just to understand the parts of a dissociation and then the constant. So a constant is just equilibrium constant if it's an acid or a base, just weak. Okay, so in order to completely determine hydronium and hydroxide, you've got to write a dissociation reaction where you create either hydronium or you create hydroxide. We're not going to have a dissociation where on one side you have both hydronium and hydroxide. So if it's a base, it'll create hydroxide. If it's an acid, it'll create hydronium. So the first step in all of these problems is always going to be write its dissociation in water. So if we go back to our previous section, one of the things that we dissociated was lithium hydroxide. So what is the dissociation? This is an ionic compound. What is the dissociation of lithium hydroxide? That's ionic. Whenever ions have dissolved, they create the positive and the negative ion. So if this was from the previous week, and we also had it on the first page of this week. So you should have split apart lithium and hydroxide. And so this is just an ionic dissociation. If the anion that dissolved is a hydroxide, it automatically is going to create hydroxide. So you would write the lithium hydroxide. This is not solubility. It's dissolved. So it dissolved. This is not a solubility problem because it is a solution. From the previous section, if it has a molarity, that means it's a homogeneous mixture. It's all dissolved. And so that creates lithium, aqueous, and hydroxide in a 1-to-1 ratio. So anything that creates hydroxide is a base. So again, I specifically put the dissociation of a weak base as needing the definition of it gains a hydrogen, it forms hydroxide. This is a strong base, just ions. Okay. So when we're looking at one of these, this is a solution has already formed, so we have a molarity. This is not a solid situation. This is not solubility. So you're going to write the dissociation, and it's going to show either hydronium or hydroxide. And so this shows hydroxide. And we're going to set up a chart. And I've already set up all the charts for all of our examples. Okay. How you start it, the concentration of the dissolved chemical is the initial concentration. And so our concentration is 0.75 molar of lithium hydroxide. That goes underneath lithium hydroxide. Each one of these is just a chemical that is dissolved in water. And so whatever chemical is dissolved, that concentration goes underneath that chemical's formula in your dissociation as the initial concentration. And we do not have any measurable lithium or hydroxide. Okay. If it is complete dissociation, your initial concentration is the change. And so this is just a solution. It's nothing in equilibrium. And so what is our change? 0.75. There are two kinds of change. If it is something that completely has dissociated, this is ionic. All of this, and we did these charts last week also for this. If it all dissolved, then all of this has turned into ions. Again, this is not solubility of an ionic compound. This is just already dissolved. And so this would be 0.75. And it's a 1-to-1 ratio. because it's the ions are 1-to-1. So we create 0.75 molar lithium and we create 0.75 molar hydroxide. And so once it's all dissolved, we have no more lithium hydroxide bonded to each other. We just have lithium surrounded by water and hydroxides. Okay. So our goal in a chart is to figure out either how much hydronium or how much hydroxide. Again, a chart will only give us either hydroxide or hydronium. Okay, so with lithium hydroxide, we have 0.75 molar hydroxide. Okay, and I put ends because it's not equilibrium. If something completely dissociates, and the only things that completely dissociate are if it's an ionic compound that has completely dissolved, again, not solubility, or if it's a strong acid. Everything else is weak. Okay. So here's our next example, HCN. And so our formula that is going to dissociate is HCN. This is one of the ones from the previous week. But for all the things that are either strong or weak acids or a weak base, which is everything other than the hydroxides, you would put the formula of the thing that's dissolving or that has dissolved plus water. And then you just have to decide, is it a strong acid, or weak base? Those are just your choices. Okay. So is it a strong acid? No, it's not. Okay. Is it a weak acid or is it a weak base? It's a weak acid. How would we know it's a weak acid? It has nitrogen, and I had said earlier that things with nitrogen, it could be, not everything that has nitrogen is a base. How would we know that this is an acid, a weak acid? The hydrogen's out front. And then the other thing is, if you look in the appendix H, you will find HCN. So if it's a molecule and it's not in the weak base chart, it's going to be the weak acid. But HCN is called cyanic acid or hydrogen cyanic acid. So this is a weak acid. The other thing, you should have written this dissociation at the end of week 4. It was in the weak acid section of the homework. So a lot of the ones that I have chosen are ones from the previous week. So, okay, it's weak, which means there is an equilibrium. And so then you have to remind yourself how to write an acid dissociation. So the first thing you do is write the appropriate dissociation, which is it ionic, or is it something that is just doing the acid dissociation or base dissociation? So an acid dissociation is a substance that loses or donates a hydrogen. So if this formula donated a hydrogen, what would the formula of its conjugate base be? CN. And the charge on CN? -1. It's a cyanide. Okay. Acids form hydronium in water. So this is the weak acid dissociation. So the acid part is it donates a hydrogen, forms hydronium in water. The weak part is the equilibrium arrows. So weak is equilibrium arrows, and then acid is what to do with this molecule here. Okay. Set up a chart. I've already set it for you. The initial concentration of your dissolved chemical is your initial amount. And so what would go underneath HCN? 0.75. Okay. If it is complete, then that is going to be your change. If it is equilibrium, is this equilibrium? Yes. Then the change will be X. Okay. So how much HCN dissociates? Minus X. We don't know. Okay. Water is a liquid. You don't have to worry about it. It does participate, but it's not going to be part of our expression. Okay. How much cyanide and hydronium are there before it dissolves? 0. And so how much change occurs? Plus X and plus X. So at equilibrium, we have 0.75 minus X and X and X. Okay. So at equilibrium, we will have X amount of hydronium, which is we want to be able to determine how much hydronium. Is X a number right now to us? No, which means we would have to do a calculation. Okay. Equilibrium dissociations. Equilibrium always has an equilibrium expression. So see if you can write the equilibrium expression for this. Equilibrium expressions are always products over reactants, and you only include aqueous things because these are not pressures, these are not gases. Everything is aqueous, how it behaves in water, so it's just aqueous. This is what your expression should look like. Your products, which are the conjugate base and hydronium, times each other, divided by your weak acid, and it's equal to the constant. Okay, but I'm actually going to put a little letter with the K. I'm not going to say KC, even though it is based on concentration. Does anybody know what letter I'm going to put for that K? YA. This is the weak acid behavior. So if you set up an acid dissociation, you would then write a Ka expression. So instead of calling it an equilibrium expression, I'm going to call it a Ka, which is equilibrium expression. So if it's a weak base, I would set up a Kb expression. A Ka expression is always going to have your conjugate base times hydronium, because if it is the acid behavior, the acid molecule or acid ion will turn into its conjugate base and hydronium in water. and it will be divided by the original thing that was losing the hydrogen. We do not put water in. Why not? It's a liquid, and water's not pure because it's part of the mixture, but our constant is based on it behaving in water. Our concentration is based on the amount of water we have. So water has already been factored in. Water is factored into the constant we use, and it's part of the molarities. So it's already there. Okay. So in order to do this calculation, what do we have to know? We have our equilibrium amounts, which would go here, here, and here. What else do we have to know? What did we spend the entire previous page figuring out? Acid constants. So I did it on we did it on the previous page because I wanted you to understand how and where to find it. So where are the two places that you would, what two places would you use to find a constant that was a Ka? Either you would look up this formula in the Ka chart, or you would look up its conjugates in the B chart and calculate the A. Okay, so is HCN in the Ka chart? Should be. That's Appendix H. (4.9 times 10 to the negative 10). That is really small. That is a really, really, really small number. The smaller it is, the weaker the acid is. And a weak acid is one that does not easily lose a hydrogen in water. Okay, so that would be equal to the concentration of cyanide at equilibrium, which is X, times the concentration of hydronium at equilibrium, which is X, divided by the initial concentration minus X. Okay. So if we do this math every time, it's every time. How often? Every time. It's going to look like this. If it is weak acid or a weak base, it will always be the constant for that acid or base behavior is equal to X times X, because you're going to make equal amounts of conjugate and then the hydronium or hydroxide divided by your initial concentration minus X every time. And this will result in your denominator being multiplied by your constant, and that being equal to X squared. And that would give us a number, an X, and an X squared, which would then go to using the quadratic equation, unless there was some way to simplify the math. Is there a new math simplification that will make your math be done just like that? Because the math is always the same. Okay. When can we simplify the math, and what can we do to simplify the math? When there is an initial concentration, which there will always be an initial concentration because we have a dissolved acid or a dissolved base, then you can ignore the minus or the plus X from that initial concentration in what condition? Go back and look at your notes from Monday. What is the, I want you to be able to like know where to look in your notes, and you'll repeat it here. There has to be a very specific situation. And what I said on Monday for KSP is going to be the same for KA and KB. Whatever constant you have here in all of these, how it behaves in water situations. If your constant is what? Small. How small? -4 or smaller. Is -10 smaller than -4? Yes. Then you can ignore what part of the change? You can only ignore the minus or plus from the any initial concentration. And so that would be this one. You cannot ignore going from nothing to something. So if you have a 0 plus X, you can't have a 0 minus X. Any 0 plus X's, you cannot ignore those, because going from having nothing to having something is a huge change. So we can ignore this. So our math ends up being 4.9 times 10 to the -10 equals X times X over 0.75. Most of the weak acids and weak bases have constants that are -4 or smaller. Not all of them. Like phosphoric acid, it was -3. You cannot do this shortcut. Oxalic acid was -2. You could not do that shortcut for that one. Okay, so if you can do the shortcut, your math ends up being the constant times your concentration square root, because it's going to equal X squared. It's really, the math is really fast. And this will give us not our answer, it will be hydronium, which we can then use to find pH. Okay, so 0.75 times this. And then you do the square root. At 1.9 times 10 to the -5.
Oh, yeah. I run to that too.
Okay, that is X, and X is, this is the one we want right here. Your goal in one of these charts is to figure out the amount that you have either at equilibrium or at the end of the complete dissociation. And so we've got hydronium is 1.9 times 10 to the -5 molar. We can then use hydronium to find the pH, because pH equals negative log of hydronium. Okay. So what I want you to do, so before, we need to add another column to this. I accidentally deleted a column when I should not have. Or maybe I was cut and pasting. So there's supposed to be another column, because all the acids are going to be the acid plus water, and the weak bases will be the weak base plus water. But this is strong. And so what's true about strong acids? They're not in equilibrium. Okay, so each of these charts that we have remaining here, and then this one here, this one, see, I have equilibrium right there. This is equilibrium, and this one is a to the end. So this is, I put these notes up here because I want you to use them. So you will write the appropriate dissociation and put the chart, and you got to decide if it's complete or if it's equilibrium. And I've used the word end and equilibrium to kind of give you a hint of which to do. If it is complete, then it goes, all of this turns into the product. And then if it is equilibrium, you're going to have to do a equilibrium expression and solve for X. Okay. And so this one here, CH3, NHCH3, it's the other. So, see if you can do, this one and then this one right here for Monday. And I want you to look over this like the information for the rest of it, because we're going to finish the rest of the stuff on Monday, which is the ion stuff. The ions, these are the ions that you should have already figured out if they're acids or bases. And you should be able to do the first bit of the homework. The first part of the homework is one of those Ka, Kb charts with the conjugates in the middle. You should be able to go ahead and do those. But for both of these tables, write the dissociation. All of these things are going to be acids or bases. Write the dissociation and then fill in the chart using the guidelines. I did one way and one equilibrium here. If it's a base, it would be a Kb. If it's a strong acid, it does not have a constant because it's not an equilibrium. Okay.